nanoHUB-U, online instruction.
Welcome back. I'm Professor Rickus. We're going to continue our discussion of feed-forward loops. In this lecture, we're going to look at a particular subtype of feed-forward loops, type 1 coherent feed-forward loops. We'll look at the behavior, both the on and off kinetics. We'll look at some of the features of why this is useful in a cellular system. And we'll take a look of an example of a real system and compare real behavior to what we predict from our models. So to remind you of our 8 different types of feed-forward loops, we had 4 coherent and 4 incoherent. The coherent, where both the direct and indirect path have the same effect on our output gene, our output Z gene here. We're going to take a look at, in particular, the type 1 coherent feed-forward loop with and integration in this, circled in this red dots here. And to remind you, this was one of our subtypes that is often enriched in biological networks, including bacterial, E. coli, and yeast transcription networks. So as we've mentioned before, oftentimes our transcription factors are regulated. That is, they're rendered active or inactive by other signals. These signals could be protein phosphorylation of our transcription factor or small molecule binding. So we're going to represent this in our feed-forward loop now with these signals, signal X, that activates Y. We designate our active form of X as an X star. And we'll designate our signal SY that activates our Y protein and transcription factor. And again, the Y form that's active will be designated with a Y star. So a naturally occurring example of this type of type 1 coherent feed-forward loop is a arabinose control system in E. coli. In this system controls the arabinose operon that controls arabinose transporters and other enzymes involved in arabinose utilization. And it responds to 2 different signals, cyclic AMP, which is an indicator of an absence of glucose, and arabinose, an alternative carbon source for glucose. So let's take a closer look at the molecular level of the AND integration. So here we've got a gene cartoon, a gene representation of what's happening in our feed-forward loop. So if the gene product of X that can get activated by our signal X, so we've got our active transcription factor X, designated by X star here, which can bind upstream in the regulatory region on gene Y and activate expression of gene Y product Y. Now, Y can also be activated by its signal. And what's important here for the AND integration, one way that AND integration can occur at the molecular level is that this would require both the binding of active transcription factor X and the binding of active transcription factor Y. So both need to be present in order to get our gene product output Z. So taking a look at this from our logic model point of view and truth table, Y now, the expression of Y over time, is going to be dictated by our simple activation equation that we looked at previously. So when our test statement, when our activated level of X is greater than a threshold value that's required to activate Y, we get production of Y, and then we have our decay term here represented by our decay parameter alpha sub Y. Now for our Z, in order to represent our AND integration, both of these test statements must be true. Both our active level of X must be greater than a threshold value in order to activate Z, and our Y star, our active form of Y, must be greater than its threshold for activation at the Z gene. And again, we have our familiar term of our decay rate in this case for our Z, alpha sub Z. So both of these statements must be true. So we multiply these, and looking at our truth table then, only when both of these statements are true, represented by 1, is our production term on, and we get an outcome of Z on. So again, both Y and X must be in their active form at sufficiently high levels. So this makes our type 1 feed-forward loop with AND integration a coincidence detector of two signals. If signal X and signal Y are required to activate X and Y, now our circuit acts as a coincidence detector of these two signals, SX and SY. So let's take a little bit closer look at our on and off kinetics of our circuit now. So just like we did with simple activation, we're going to look at the dynamics to turn the system on in the case of strong activation. So initially our system is off. So before time equals 0, we have no activated X around. And then at time 0, all of a sudden we have an instantaneous increase in our X star active form of our transcription factor, and it is well above our threshold. So we're going to look at the time it takes to turn our system on when it's maximally pushed to being on. And then we'll also take a look at the dynamics to turn the system off. So in this case, we'll start with our system initially fully on, and at time equals 0, we'll instantaneously take away our X star value down to 0, well below its threshold for activation, and look at the time course for turning our expression system off. And one of the key things we want to know is what is the response time for both Y and Z to turn on and off. And so for looking at our extreme case of very strong activation, we're going to assume that there's lots of SX around so that all of our X is in its X star form. So let's first take a look at the Y response time. Okay, so I'm going to focus here in the red dash. We can see that turning Y on is our familiar simple activation. So if we go back from our previous lecture and remind ourselves our case of strong activation, then at time equals 0, our expression of Y will turn on, and we'll follow our time course here. We've got our beta over alpha, which is our steady state level that we're going towards. And our alpha Y is going to determine how quickly that decay parameter is going to tell us how quickly we approach that steady state value of beta Y over alpha Y. And we define our response time as the time that it takes to get halfway to our steady state value. And we designate that T1/2. Now that we've got multiple components going on in our circuit, we'll be sure to indicate T1/2 Y, indicating that we're talking about the half-life, or the response time for turning Y on, as opposed to other genes in our circuit. And if you recall, our response time of simple activation is simply the natural log of 2 over our decay rate, alpha Y. But what we really also need to know when Z turns on is that we need to know how much time it takes for Y not only to get halfway to its steady state value. What we need to know is how long does it take to reach its threshold value in order to turn on Z. So we can find this time that we'll now designate T on using a similar method. So looking at our similar time course here, now we're interested in the time T on that it takes to get Y not to half our steady state value, but to our threshold value for activating gene Z transcription. Okay? So we can find this time in the usual way. We can, by simply plugging in Y at time T on equals our threshold value KYZ. And when we do that, we get this expression here. And we can see that this time it takes to reach that value is now not only a function of our decay rate and our steady state value of our Y gene product, beta over alpha, but also our threshold value, KYZ, for turning on Z. So now let's look at X, Y, and Z together across time. So again, reminding you, our X before time equals 0 is at a 0 level. We instantaneously turn on X star to a level well above its threshold and a constant value. As we said, Y is going to turn on with simple activation. And so immediately at time 0, our gene product Y starts to accumulate. And now we know the time at which Y reaches its threshold value to activate Z. And remember, X is already well above its threshold value. And we need both X and Y to turn on Z. So Z will not turn on until Y also reaches its threshold value. So we have a delay here. So this T on value now becomes a delay. And Z doesn't turn on until X and Y are both above their thresholds. Once Y reaches that, now Z expression turns on, following our simple activation time curve. And we now can look, our simple response time will be this time window here. That would be the time that it takes Z to turn on, or to reach half its steady state value from the time it actually comes on. But if we consider the response time for the entire system, the total response time for Z is now the delay plus that time for simple activation. So why might a delay in our system be useful? Well, there's several reasons why this would be useful. And one way to look at this is if we consider what if X comes on and is not a permanent step change, but rather a transient step change. In other words, we have a short input signal. And let's look at the extreme of when we have a short input signal versus having a longer persistent input signal from our X value. So if SX is only around temporarily to turn on X to its active state, then if it may not be on long enough to accumulate enough Y in order to turn on Z. So if that SX is short, so short that we never get enough Y to reach its threshold, Z will never come on. In contrast, if our signal for X is persistent and is on for a longer period of time, long enough such that Y can now accumulate to reach and surpass its threshold value for turning on Z. Now we see Z come on. So now our circuit is acting like a persistence detector. So it only responds, we only get output if the signal SX is persistent. And this might very well be useful to filter out flicker noise. If SX, for example, is a noisy signal, or imagine there's a very high cost of being wrong in turning on an error, then we would want to filter out that erroneous noise that's not really meaningful or biologically relevant to the cell. And so now what is long enough, you see, is relative. Determining how long it needs to be on is relative to whether or not we reach our threshold. So we can tune this delay now and therefore tune our filter. So let's take a look at the design equation. Let's go back to our equation for T on. And this is really now for tuning our delay. T on is our delay. So this becomes our design equation for how we would tune that persistence detector or filter. And now we point out we have 3 tuning parameters to set that delay. We have alpha Y, related to the protein half-life, that is the decay rate of our protein Y. We have our threshold for transcription activation of Z by Y. And we also have our Y steady state value, which was our beta y over alpha y, which I've now just substituted in and called y steady state. So we have these three parameters that we can now tune: alpha, beta, and alpha, which contribute to our y steady state, and our threshold value. Now, if we rearrange this just slightly and look at our delay as a dimensionless delay. So I'm just going to move this alpha term to the other side. And now this alpha y t on is really a dimensionless delay. It's a delay that's relative to the y decay rate. And now we can see what's really important in this equation is the ratio of the threshold of turning on, right? Which is going to be a level value of y relative to the steady state value of y. And so now this ratio we can view as a dimensionless threshold. It's the threshold of y to turn on z relative to the steady state fully on value of our y gene product level. And I'll take a second here to take a look at the equation and think about what happens from the equation standpoint of view, and then why does that make sense? What happens if our threshold is greater than our steady state value of y? So pause the video and just take a second to look at the equation and think biologically why that makes sense. Okay, now that should become more clear now when we look at our design equation as a design curve. So what's plotted here is the dimensionless delay, alpha y t on, versus our dimensionless threshold. So our threshold relative to the steady state value of y. And this is now our curve. If we want to tune our delay, this is our curve that tells us how our tuning parameters will allow us to get the delay that we want. And if we notice, if KYZ gets bigger than our steady state value, y star will never reach the threshold, right? So Z would never turn on. So that would be an important parameter. This is a great example of why thinking quantitatively about gene circuits is critical, because just because you put together some transcription factors in a feed-forward loop doesn't mean that it would behave like this. If, for example, if you didn't pay attention and you designed a system where your threshold value was greater than your steady state value, it certainly wouldn't behave as if you expected it to for our feed-forward loop. So now let's take a look at what happens when we turn our system off. Again, we're focusing on our type 1 coherent feed-forward loop with AND integration. Okay, so now if we start with the system fully on, so we have maximum amount of our X star, our Y star, and our gene product output Z. So everything is on. And if at time 0 now, we instantaneously take our activated X transcription factor away. Well, Y is turned on by simple activation here. So when X goes away, our transcription will turn off, and we'll simply have a decay that's dominated and controlled by our decay rate, alpha Y, of our Y protein. So now we look at Z. Now remember, we have AND integration here. So both X and Y are required for Z to be on. So as soon as X goes away, even though Y is still above its threshold, Z will immediately turn off because we have no X. So in contrast to our on kinetics, we have no delay in our off. So we have a system that has asymmetry in its delay. A delay in the on, but a delay in the off. Both Y and Z look like just simple activation off kinetics determined by their relative decay rates, alpha Y and alpha Z. So this is all great, but we've just been really talking about a theoretical circuit. And none of this is of really any value at all unless we see real circuits that behave the way we expect them to. So let's go back to our real natural system that we mentioned, the arabinose utilization system, right? So E. coli prefer glucose as a carbon source, but they can use arabinose. So the cell is only going to want to turn on all the machinery for arabinose utilization when glucose is unavailable and when arabinose is available. Otherwise, to just turn on all the arabinose transporters and all the arabinose catabolism genes when it's not needed would be a waste of cellular energy. So this system acts as a coincidence detector. As we mentioned before, cyclic AMP levels are inversely related to glucose levels. So when glucose is absent, we have more cyclic AMP around than when glucose is prevalent and we have less cyclic AMP. So now cyclic AMP is an indicator of an absence or lack of glucose. So now this system acts as a coincidence detector of cyclic AMP, or lack of glucose, and arabinose present. So if we look at our truth table now, only under the condition in which cyclic AMP levels are high and arabinose levels are high, meaning glucose levels are low and arabinose levels are high, does our arabinose system come on. Okay, so the question is, does the real system behave like we expected? And these experiments have been done. So what people did was, so they took the natural arabinose utilization system and compared it to a simple circuit with AND integration. And asked the question, what does the model predict? And how does the bacteria's behavior compare to the models? So when they did this, and using just the same equations that we've been using to talk about simple activation and feed-forward loops, if you look at the levels of our output Z over time, measured by, in this case, the arabinose output operon genes, or in this case, a signaling reporter was put on, GFP, on this system as an indicator of output. And now you compare the simple in the red dots and the feed-forward loop in the solid blue line. And you can see in the on kinetics, in fact, they did see no delay in the simple system. And again, this is just our model now we're looking at. And they also did see the expected delay in our feed-forward loop. Conversely, when you look at the off situation, the model predicts no delay and it's simply both systems, the simple and the feed-forward loop, looking identical, both looking like simple off kinetics. Okay? So what about the real system? So in the experiment now, they saw the same sort of behavior. Again, so our arabinose system, our feed-forward loop, here in the open circles, right? Or excuse me, the simple in the open circles and the feed-forward loop in the closed circles. For the on condition, a delay in the feed-forward loop was observed. And conversely, in the off kinetic situation, turning the system off, we saw identical behavior in both the simple, the real simple, and the real feed-forward loop. Again, both looking like simple decay. So that's good, right? So this tells us, at least in simple and bacteria systems that we understand pretty well, that the feed-forward loop is behaving as we expected to, and our models did a pretty good job here in predicting the behavior of the system. So just to summarize just a little bit, and let's recap talking about the coherent feed-forward loop type 1 with AND logic. And again, reminding ourselves so that it has a sign-sensitive delay. In the on condition, we have a delay. in the off condition, when we take our signal away, we have no delay. And that this protects against fluctuations and temporary introduction of our signal. So this is very useful when the cost of turning on an error is high. So another example of this in cellular systems, think of mammalian cells that induce apoptosis normally during development or during stress or injury, and programmed cell death, which is a normal part of cell function. The cost of turning on cell death in error, you wouldn't want to cause erroneous cell death when it's not necessary, when the stressors aren't present, or the signals for cell death happening when they should be in order to get normal organ development, for example, in the brain or other organs in the body. You would not want this to turn on in error. So this would be an example of a type of cellular function that needs to be turned on, but the cost of doing that erroneously would be very high. So conversely, if we switch the logic at the Z gene from and to or, we switch the sign-sensitive delay. And that is, with the on situation, we get no delay. And with an off, we do get a delay. And this protects against fluctuations or temporary loss of a signal, useful when the cost of turning off an error is high. So we're going to save this one for you for a homework problem to work out on your own, similarly to as we did in this lecture, looking for OND logic. So coming up, we're going to move a little deeper into cell dynamics, and we're going to take a look at some cellular oscillations and cellular switches. I look forward to working with you on those next.